Well, welcome back. This is part 3 of our introduction to mechanical analysis of soils. In this case, we're doing a sieve analysis. So in parts 1 and 2, I introduced the concept. We talked about how to plot a particle size distribution graph. And I gave you a little insight on how to read the log scale for the sizes. So now I want to put it all together and work with a problem, or work a problem with you. So let me share my screen. And let me get the right one up. There we go. Okay, so this will be an example for how to do a sieve analysis. We'll work it through point by point. So what we want to do is from the raw data, which I'll give you in a second, we want to make the proper calculations for the percent finer for each sieve and then draw the particle size distribution graph. And then we want to find these values here, the D30, the D60, and the D10, D30, and D60. And those are the diameter of the particle that 10% is finer, and then 30% is finer, and then 60% is finer. And with those three values, you can then compute the effective size, the uniformity coefficient, and the coefficient of gradation. So there's the data that I gave you for this set of sieves. If you look in the notes, you'll see that for each sieve size, there is an appropriate diameter. On the graph that paper that you're going to use for the next homework assignment, the sieve sizes themselves are marked on the graph, so you won't have to worry about that. When we do a spreadsheet later on, you will have to put in the appropriate diameter size for the sieves. So again, here's the data again from the sieve stack, and you can see there's our raw data. So here's the example. So the first thing I want to do is calculate the percent retained on each size. Oh, it looks like I've already done that. I apologize for that. I should have brought those up slowly, but I did go ahead and sum the total and get the total in the of 617. And then I calculated the percent retained on each sieve. And unfortunately, I should have done that incrementally. But what I did instead was I went ahead and did the calculation. So for example, the first one is 28. 28 divided by 617, which is the total, gives you 4.54%. And all the way down, for example, the 100 sieve is 86 grams. 86 grams divided by a total of 617 gives me a 13.93%. So you can make each of those calculations individually, and they're not really a function of each other. So again, the interesting calculation for this, the one we talked about in the previous videos, is how do you get the cumulative percent retained? So the first one is easy. You just take the first value and you bring it over. So the first cumulative percent retained is 4.54%. So I like the second method that I showed you. So what we'll do is we'll take that 4.5, we'll add the next one, which is 681, and that will give me the next value. So 4.54 plus 6.81 gives me 11.35. And you can continue that. So the next one would be that 11.35 plus 7.78. And then the result, 19.13 plus 20.75, 39.88. 39.88 plus 35.82, 75.7, 75.7 plus 13.93, 89.63. And you just keep this up. And if you get 100 at the end, more than likely you've accomplished it correctly or done the correct calculations. Now remember, the percent finer is always 100 minus the cumulative percent. So for the first one, it will be 100 minus 4.54, gives me 95.46. And you can just keep that up as you go down the list. And you should see the number getting smaller each time. And then you should end up, in this case, 100 minus 100, we should end up with 0. So you have a little bit of a feedback that you're moved in the right direction. So now what I want to plot on the graph are my sieve sizes given by the sieve number, and then the percent finer over on the far right column. So if you get a piece of the graph paper that I've put a link on the homework page and off the notes, then you will plot that graph. And here's a plot of that data. So you can see we've got a kind of a distribution of particles. There seems to be a little bit missing in the middle. You can see it's more vertical. So there's quite a bit of fines, quite a bit of larger particles. Now remember, we're going to find D10, D30, D60. So for D10, remember that's 10% passing. So we'll find the 10% passing line. Now again, on the graph paper that you have for homework, you'll be able to see that line explicitly. You won't have to actually sketch it over. I left the grid lines off to make the graph a little less busy. And then once you find where the 10% passing crosses your graph, mark that point and then drop down to the x-axis. So now you can see that I'm looking at something between 0.1 and 0.2. I just want to emphasize that first tick would be 0.2. So it's between 0.1 and 0.2. So we know it's going to be 0.1 something, and you just have to guess. It's kind of in the middle, so I guessed 0.14. Remember, the numbers are shifted to the right, just like the scale is here. Okay, the next one we need is D30. Again, let me emphasize this. We should all get 0.1, and then the next decimal, or the last significant figure, is the one that we're approximating. I chose 4. You could choose 5 or 6 or maybe even 3, but there's a range that's acceptable. I don't think 1 and 2 would be acceptable, and I don't think 7, 8, or 9 would be acceptable. But there is a little bit of a range in there that would be acceptable for us to just interpolate. So the next one we're looking for is D30. So there's the 30% passing line. Find where it crosses the curve and then drop down to the X scale. Now here it looks like it's between 0.2 and 0.3, and it's shifted to the right. I expect a higher number there for my last digit, so I chose 7. 8 would probably be reasonable, maybe even 9, maybe even 6. So all those would be reasonable estimates, but we should all get 0.2, and remember the last significant figure is the one that we're estimating. And then finally D60, find the 60% passing line, hit the curve, and drop it down. In this case, it looks like it's between, let's see, that's 2, 3, 4. So it looks like it's between 0.4 and 0.5. So it's going to be 0.4 something. And it's towards the left edge. So maybe 4.2, 4.3 would be reasonable. Yeah, I chose 4.2. Now your work is done. The remaining calculations are pretty straightforward. So I went ahead and just reminded what those values we interpolated from the graph are. Remember, the effective size is just D10. So the effective size of this material will be 0.14 millimeters. The next calculation would be the uniformity coefficient, which is defined as D60 over D10. So for this interpolation, it was 0.42 millimeters over 0.14 millimeters. Notice that the units cancel, and we have a non-dimensional number, 3. So what it's saying is really as you move closer and closer to 1, your particles tend to be more uniform. And this is farther away from that, 3. So these are, we have quite a few different particle sizes in this. And then finally, the coefficient of gradation is D30 squared divided by D10, D60. And we put our values in there. Again, you'll know you've got millimeters squared, and then 1, 2 squared in the denominator. So again, we get a dimensionless number, in this case, 1.2. So if you can do that for your homework that's coming up, that would be great. And also, as we move towards the final exam, you'll have problems like this on the exam. Not only to make the calculations, maybe to do a quick plot, or I'll give you a plot and you'll have to interpolate D10, D30, D60. And then from that data, or from data that I give you, be able to calculate uniformity coefficient, coefficient of gradation, and know the effective size. Okay, so as always, let me know if you have any questions. Best way to get me is through email. I'll stop sharing my screen. And again, just let me know what's going on out there. I don't have any contact with you guys. I'm not sure. So send me an email or let me know if we need to have a Zoom meeting on some of this. We can do that. So until next time, take care and be safe.